Okay, so let's go ahead and get started. Okay, so at this point, we know that a chemical equation is based upon A, quantity, B, mass, C, whatever I feel like that day, or D, whatever you feel like that day. Okay, those who say A, quantity, raise your hand. Chapter 2. They'll probably need 14 as well too. Okay, so at this point, we know that a chemical equation is based upon A, quantity, B, mass, C, what I feel like today, D, what you feel like today. So those who say A, raise your hand. Those who say B, raise your hand. Okay, so you guys are already doing great right now. A is the correct answer. We know C was a bunch of BS and D was a bunch of BS, right? So we know that it is based upon quantity, right? Because we know here, this tells us if we had 4 ammonia and we have 5 oxygen molecules, we can make 4 nitrogen monoxide and 6 waters, right? So, and we know that because the chemical equation is balanced, right? So we also know that if we know these things, we can use them to calculate how much we can make, right? Because we can use the ratios, right? So we know that for 5 moles of oxygen, we're going to need to have 4 moles of ammonia. Or we can flip it around. We can say 4 moles of ammonia, we're going to need 5 moles of oxygen, right? That's right. It's that mole to mole ratio. Okay. That's good. That's good. That's a bonus. Okay. So now what I want you guys to do is, if you guys have 3.2 moles of ammonia reacting according to the equation that we just showed, how many moles of water will we produce? So where are we going to start at? The given. Okay, our given was 3.2. .20 moles. Of ammonia. Okay, since we're already in moles, what are we going to do now? We're going to use the ratio. So what is the ratio of ammonia to water? Okay, so for every 6 moles of water, we're going to have 4 moles of ammonia. Okay, moles of ammonia are going to cancel out. And then we're going to be left with I don't have my phone with me. Who's going to do the heavy lifting? Okay, how many sig figs should I have? Just 2. So how many did we start off with? 3 point. Okay, so we know that we're not going to use this ratio to determine. We're only going to use what we started out with. So we should have 3 sig figs, right? So okay, piece of cake, not too hard. Okay. Questions? Concerns? Cash? No cash? I know I'm broke too. Paying all these damn bills today. You're not broke? No? Oh, okay. I should be begging her, huh? Is that what you're saying? Okay. So we know if we have quantity is going to be in moles, right? Then we can use that mole to mole ratio to get how much of our product that we have. So if we know our reactants, we can figure out how much product we're going to make, right? That makes sense, right? Does make sense or no? Okay, good. Okay, so let's keep doing this, right? So how many moles of oxygen are required to burn 2.40 moles of ethane? First thing I need to do is to do what? We can use our given, but what are we going to use a given for? We need we need our chemical equation. That's right. We need our chemical equation. Good job. So, so we did a lot of that, yeah? I give you that exam. It's so much fun, isn't it? Do you guys ever want another take-home exam after that? No, you're good. You're like, I like the multiple choice. Okay, so what are we going to do about this chemical equation? So what do we know? What are our reactants? Ethane, okay. So we know ethane, which is C2H6, and oxygen, which is O2. Why is oxygen O2? What was that?
The diatomic.
Diatomic, that's right. Good job. Okay, and what are we making? What do we know we always make when we burn stuff? What gas do we make? CO2 and water. That's right. So when we burn hydrocarbons, we're always going to get CO2 and water. Okay, is this balanced? No. What do I need to do to balance it? Okay. CHO. Okay. How many carbons do I have on my reactant side? How many do I have on my product side? How many hydrogens do I have on my reactant side? How many hydrogens do I have on my product side? Oxygens on my reactant side and on my product side. 1, 3. Okay. So is that balanced? No, it isn't. So we're going to put 3 in front of the H2O. Okay, so that gives me 6 H's. And then how many O's am I going to get? 5. That's correct. Okay, is it balanced? Okay. What else do I need to do? What about my carbon? What do I need to do with my carbon? So how do I balance it out? What do I need to do to balance it out? I need to put a 2. Put a 2 in front of where? This here, right here. Okay. So on the product side, so then that gives me, and then how many oxygens do I have now? I have 7. Okay, so is that balanced? What do I need to do to balance it? On the other side, what am I going to do? So how can I get 7 if I have 2? I can't. If I put a 5, so what if I put a 7/2? We could do it for right now. So will that give me 7? It will give me 7. 7/2 times 2, that will be 7, right? Okay, so, but we know that if I decide to cut out Lorenzo, right, cut him in half, is he going to be okay? No, he's not, right? So we can't cut a molecule and it'd be okay. So what we'll do is multiply the whole thing by what? 2. So if we do that, we have 2 ethanes plus 7 oxygens, gas, yields 4 carbon dioxide plus 6 waters, gas. Okay. So now we have a balanced equation. So can I use this to determine how many oxygen molecules I need to react with my ethane? I can't. So as he was saying earlier, David told me I need to start with my given. So I have 2.40 moles of ethane. So how am I going to use that equation I just worked hard to balance? I'm going to use the mole to mole ratio. So 7 moles of oxygen and 2 moles of the Fa. Oops. Bless you. Okay. Who does the heavy lifting? $8.4. How many sig figs should I have? 3 sig figs. I know it only has 2 on the handout, but okay, questions? Good. Okay. Everybody got it down? Good, good. Okay, so if we're trying to get to mass, we know that we can use the molar mass to get to the moles. And we know that we have to get to moles to be able to use that equation, right? So if we have the mass of what we're given, we can calculate the mass of what we want by using the molar mass to get to moles, and then using that mole to mole ratio to get to the mass of what we want. Okay? So let me give you an example. This is just another schematic that basically shows you exactly the same thing. If you're given the mass, you have the molar mass, you can get the number of moles of our reactant. We can use the mole to mole ratio to get the moles of our product, right? And then we can use that and the molar mass to sit there and get the mass of what we want of our product. Okay, I'm also going to tell you something else. So we know that, what are the units for molar mass? Anybody? Grams per mole. So we know that it's grams per mole, right? Now, you guys remember when you learned those Greek prefixes for like kilograms, milligrams? Okay, so if I have grams per mole, right, that's like that, whatever that value is. Like say, for instance, carbon. Carbon is 12 grams per mole, right? So I can also say carbon is 12 grams per milligram per millimole, right? Long as I have that prefix on both of the top and the bottom, that ratio is going to be exactly the same, right? So whatever value we have, it's always going to be the same. Do you guys understand what I'm saying? Or do you want me to write it down so you guys can see it? Okay, so let me say, so for instance, we were talking about carbon. So carbon weighs how much? We know it weighs 12 grams per mole, right? So if carbon weighs 12 grams per mole, carbon also weighs 12 milligrams per millimole. Carbon will also weigh 12 kilograms per kilomole. So as long as the units, that that prefix matches the prefix in the bottom, this value is going to always be the same. It's always going to be 12. Okay? So the reason I'm telling you this is because here we're solving for milligrams, and we want to get, we're starting with milligrams, and we want to get milligrams at the end. So we don't have to make that conversion of changing milligrams to grams, right? So I'll read the question. How many milligrams of nickel 2 chloride are in a solution if 503 milligrams of silver chloride is precipitated in the reaction of silver nitrate and nickel 2 chloride solution? Okay. So first thing I want to do is to do what? I want to write a balanced chemical equation. So what are my reactants? Silver nitrate. So what is the chemical formula for silver nitrate? Silver nitrate is AgCl. AgNO3. Because I asked you, what are the reactants? Right? Because we know that the silver chloride is the product, right? Okay, and we know that these are solutions. So what does that tell me? They're aqueous. So we have silver nitrate reacting with nickel 2 chloride. So how would I write the chemical formula for that? NiCl2. And again, we know that's aqueous. Now, what are the products? AgCl. Okay, it says it's a precipitate. What does that mean? Solid? Okay. And what is going to be my other product? Nickel nitrate. Nickel 2 nitrate. NO3 and parentheses 2. Okay. And since they didn't say anything about it, we're going to make the assumption it's going to be aqueous. We can check it out though, because we also know that anything that's with nitrate is going to be aqueous, right? Okay. Is it balanced? No, it isn't. Okay. What do I need to do to balance it? I hear two in front of the silver nitrate. Okay. And 2 in front of the silver chloride. Okay, is it balanced now? Okay, so we're good to go. So now we can start with our given. So we have 503. Milligrams of silver chloride Okay, so how do I go from milligrams to millimoles? I use what? Molar mass. I use my molar mass, right? So I don't have to convert it to grams because I can take that little cheat step when I go milli in front of milligrams over millimoles, right? So first off, how much does silver weigh? And how many silvers do we have in silver chloride? We have 1, right? 1 silver, and it weighs 107.87, right? Okay, and I have 1 chloride, and that weighs 35.45, is that correct? So I add that together. Two, 3, oops, 140, right? That's a 4. Okay, so, and I can use milligrams over millimoles. Because they both have that milli in front, so that would just kind of cancel each other out, right? So 143.32 milligrams of AgCl will give me 1 millimole. AgCl. Okay, so we've gotten rid of milligrams, and now we have millimoles. So then, if I want to figure out how much nickel 2 chloride I'm gonna need to make that, what am I gonna do? My mole-to-mole ratio. So what is the mole-to-mole ratio of nickel 2 chloride to silver chloride? So I have 2 millimoles of my silver chloride at the bottom. And then I have 1 millimole of nickel chloride, nickel 2 chloride at the top. But I want grams. So now I have moles, right? Millimoles. How can I get to milligrams? I heard somebody say it, molar mass. Is that what I heard? Okay, so I want the molar mass of nickel. So what is the molar mass of nickel chloride? Nickel weighs how much? 58.693. And then we know that we have 2 chlorides. So it's 2 times 35.45. Which is going to equal 70.9. I'm going to add those together. So yeah, 9. Let's see. So 129.593. That's milligrams per 1 millimole. Okay. So it's going to do that heavy lifting. What you guys get? $227 milligrams of nickel 2 chloride. And it's the right sig figs too. Excellent. Good job, Aaron. Questions? No questions? I know my head's in the way. You don't have to put the AQ for here. Yeah. Just you only need it for the chemical equation. Yeah. But that's actually a good question. Nice catch. Where's mine? Okay. Questions? Concerns? Cash? Kool-Aid? One day, if I ask, one day it's going to happen, right? Exactly. Oh, what is it? It's square. Yeah, it's called square. Yeah. Yeah. That's actually a good idea. Great idea. Okay. So you guys ready to move forward? Ready for some more exciting stuff, right? Yeah. Okay. Okay. So did I tell you my ideal yield story? I told somebody the story. I always guess the summer, but that doesn't count. This class, I haven't told you the story. Okay, so let me share the story with you. Okay, so I've had a couple of instances in my life where I thought I was going to quit science. One of them has to do with ideal yield, right? I was actually in a class called quantitative chemistry. Quantitative chemistry is actually using a lot of analytical chemistry, not quantitative chemistry. Analytical chemistry is using a lot of equipment to sit there and determine how much of a chemical compound that you either started out with or a product that you ended with. And one of the projects was to try to figure out what we started out with. And so I went and I did the experiment, and I was just going. And let me say, this was in my second year of chemistry. My first year of chemistry went perfect. Straight A's. I was in honors chem and everything like that. I kicked ass, right? Very proud. I was, kind of big-headed, cocky and everything. So I go in the second year, I'm like, I own this place, right? It's going to have my name written on the side of the building, right? That's the way I was thinking. I'm like, okay. So I go in and I'm like, bam, 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 bam. Did my calculations, and then I get 86.7% yield. And I'm like, that's a B. That's not an A. That's not acceptable, right? I need to get 100%, right? So I did it again, and I'm quick. I'm like, bam, 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 bam. Okay. 86.5. What the fuck? Wait, it's getting worse. It's not getting better. What's going on? Right. So I'm getting a little upset. So I go over everything and I'm like, hey, make sure all my chemicals are right. Everything. Okay, let me try this again. 86.7. At this point, I'm really pissed off. I'm a little hangry, right? I'm hungry at that point. I'm upset. And I'm like, okay. So I go to the TA and I'm like, is there any way that I can come back later on? Because I didn't finish the experiment and do it again later tonight. So he's like, yeah. So I go back, get my book, do all my calculations all over again, go grab something to eat, and I eat when I'm stressed, right? And at this point, I'm a little stressed. So I ate quite a bit. And I'm like, right? So get to the lab. And then, I forgot to say, there's another student there. He's a really rich kid, right? One of those kids that, had everything handed to him his entire life. When he got to college, his dad, since he went to college, and got accepted to his dad alma mater, his dad also donated a building to the school, right? So he decided that he was going to come and do the lab, right? He finished as well, right? In the evening. And so I'm like, okay. And anyway, and he was going to be a chemist major, but he never showed up to class. He had a tutor that did his homework and all of those things, right? So he's that type of kid, right? So anyway, we both end up going later on and stuff like that to the lab, and so then I go ahead and I do it again, and I'm working. All right, and I get the same answer, 86.7. I am upset, right? And I'm like, okay, getting a little pissed off here, right? So, and he finishes up, and I'm like, what did you get? Oh, I got 100%. And I'm thinking to myself, if this fucking idiot can get 100%, I should be, perfect. What the hell? What's going on? So, you know how you talk to yourself and you're like, if I don't get it this time, I'm done. I just quit. I'm it, And I'm like, and it's kind of like that pressure that you put on yourself to make sure you get to that point, right? So I'm like, okay. So I go over it one more time, check everything one more time, and I'm like, I'm getting 100%. If you got 100%, I can get 100%. I go and I do it. Bam, 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 bam. 86.7. I am livid. I am so pissed. I throw my lab notebook across the room into the garbage can. I am pissed. I'm fussing. I'm like, God damn it. Done, right? Get up, walked out, kick the garbage can, right? Slam the door. And the TA looks and he kind of, what the hell's going on, right? And he's looking at me as I'm walking out the door and he's like, and he just took the time. Mr. Henry, what the hell's wrong with you? I did the experiment. I did it perfect. I think I'm just not cut out for chemistry. I did it perfect. And I kept getting 87.6%. And he laughs, right? And I'm pissed, right? I'm like, this motherfucker's laughing at me, right? So I'm like, ready to fight almost. And he's like, Mr. Come in the classroom. So I go in the classroom, take you to the back room where all the chemicals at. And he said, why don't you take a look at this? I look at the back of the chemistry, the chemical, and it says 86.7%. At this point, I feel like a fucking idiot, right? Because I'm like, I'm getting the right answer, right? But it was 86.7%. So there's a couple of morals of this story. One thing, what was that? Don't listen. Exactly. Don't listen to rich privileged kids, right? So that was a very important lesson I learned, right? So you can't always believe what people say, right? Because half the time they're lying to you, right? And the other thing is that there's going to be very few cases where you're going to end up getting 100% of anything, right? Because particularly in chemistry, the chemicals don't react completely, right? So you'll get partial reactions. You can also get secondary reactions. You could have impurities. Somebody could have spit in it. Somebody could have peed in it, right? All of those things are going to affect the chemical reaction. And so there's very few cases where you're going to end up with 100%. It almost never happens. If you end up with 87.6%, you should be pretty damn happy, right? Okay, so when you think about percent yield, chemistry is never perfect. There's always little issues that are going to happen. Some of them are man-made, us pouring stuff down the sink, or, knocking things over, or putting acid in water, all of those things, right? Play a part in it. That is part of the process. The thing is that we always want to make note of it, and we want to calculate the percent yield, right? So the way that we calculate the percent yield is very simple. It's what you actually get from the experiment over what you've calculated, or what we call the ideal yield. And we multiply that times 100%, okay? So the actual yield divided by the ideal yield, sometimes called the theoretical yield, times 100%. And that's going to give us our percent yield, okay? So, the other thing is, the other moral is, don't quit, right? You're going to fuck up. That's part of life, right? But don't quit. Don't give up on yourself, right? And if it wasn't for that TA, I would have given up on myself, right? That was a very important lesson for me to learn. Okay, so let's test this out. A solution containing 3.18 grams of barium chloride is added to a second solution containing excess sodium sulfate. Barium sulfate precipitates. Calculate the yield, the ideal yield of barium sulfate. If the actual yield is 3.37 grams, calculate the percent yield. Okay, so where are we going to start at? We need to start with a balanced chemical equation. So what are my two reactants? So barium chloride is BaCl2. And we know that that's a solution, so it's aqueous. And you said it's sodium sulfate. What is the chemical formula for sodium sulfate? Na2SO4. We know that's also aqueous. And what are we going to make? Barium sulfate. And we know that that's a precipitant, so that means it's a solid. That's right. And sodium chloride. Good job. And we know that that's going to be aqueous. Because we know group 1 metals always going to end up being aqueous. Okay? Is it balanced? No. What do I need to do to balance it? 2 in front of NaCl. Okay, then now we're good. Okay, so now what are we going to do? Start with our given. Okay, so we have 3.18 grams of barium chloride. Next. One mole of barium chloride. The molar mass. So we need to get our molar mass. Yes, I know exactly what you're saying. So we have one barium chloride. We have one barium in barium chloride. Barium weighs 137.7. What? 137.33. Okay. And then chloride weighs, and there's 2 of them, 35.45 times 2. Okay, so that's 70.9. We add those together. So that's what? 2. To 8.23. Grams. So those grams are going to cancel out, and we're left with just moles of barium chloride. Okay, so what am I going to do next? Mole-to-mole ratio. Okay, so what is the mole-to-mole ratio of barium chloride to barium sulfate? It's 1:1. I love it when it's 1:1. Okay, so those moles are going to cancel out of barium chloride. Now we have moles of barium sulfate. How do I get the grams of barium sulfate? I need to find the molar mass, right? Okay, so we have barium again. We have sulfur. We have how many oxygens? 4. Okay, so the barium we know is 137.33. The sulfur is, say, 32. And then the 4 oxygens, 4 times 16. So what is that, 64? And we add that all together. Six plus. So what is that? So is it 223.33? Yeah. Yes. Yeah, so it's anytime that it's a third, like 0.33. So I always say if it's 0.3 and to like, 0.7, then I'm going to leave those. I'm going to use those decimal points, right? So like 0.33, I'm going to use it. But if it's like 19.997, I'm going to round out to 20, Yeah, you can round down. So if it's like 12.01, well, 12, right? If it's 12.11, 12. Yeah, yeah. Is it 223 or is it 233? 233. Okay. This is why calculators come in handy, right? Okay, so then I have 233.33 grams per 1 mole of barium sulfate. And what do you guys do? And what do you guys get? You said 3.56? Yeah. Okay. 3.56? 3.56 grams. Okay. So if our actual yield is 3.37 grams, 3.37 grams, calculate the percent yield. So how would I calculate the percent yield? Percent yield. So it's the actual yield divided by the ideal yield. Okay. Times 100. And what do you guys get? Like 94.7? So are you one of those rich, right? Rich? What was that? 97, I mean 94.7. So, but I have a great story to tell you though. So afterwards. So anyway, it was when we got ready to graduate. Um, he actually graduated and everything like that. And he actually hung out with us. He started actually doing his own work and hanging out with us and studying with us. And so when he graduated, his dad came up and gave me $100 for a graduation gift. He's like, I know that you're the only reason my son passed this class. So it made me feel good. Yes. So, yeah. I know. And he gave me $100. I know. Yeah. Yeah. It's just percent. Yeah. Nope. It's yield. It's percent yield. Okay. Questions, concerns, cash, Kool-Aid. Okay. Everybody got it down? I can erase, move forward.
Dr. Henry, I have a question.
Yes. Yes.
Don't have to put anything after 94.7%.
No, you just have to put 97.7%. Good
Okay.
question. Yes. Okay. Clear. Okay, so solid sodium will, this will be the question we'll do before we take a little bit of a break. Last question we'll do before we take a break. So we have solid sodium decomposes to solid solid sodium nitrate decomposes to solid sodium nitrite and oxygen gas upon heating. One set of reaction conditions gives 95% yield. What is the mass of the sodium nitrite will be produced by the decomposition of 1.5 grams of sodium nitrate? Okay, let's start with writing the equation out first. I like that answer. Okay, so we have sodium nitrate decomposing. What is the chemical formula for sodium nitrate? And we know that that's going to be a solid. That's going to yield NaNO2, solid. It's diatomic, that's right. Is it balanced? No, it's not balanced. Okay, so how do I balance it? I heard somebody say, ooh, what does that mean? Two, I heard two. Where am I putting the two? In front of the Na, which one? This one? On the reactant side or on the product side? You gotta talk. I can't just look and point. I don't know what that means. On the reactant side. Okay. And anything else? Are we balanced now? I need to put it on the product side too. Okay, now we're balanced. Yes, good. Yeah. Okay. Sometimes what I do is If I don't see it immediately, right, I'll take a minute. I'll go on to the next question, do the next question, then I'll come back. And then all of a sudden it'll be, oh yeah, you know, yeah. Okay, so we have a balanced chemical equation. So what are we gonna do next? We wanna start with what we're given. So we're given 1.50 grams of sodium nitrate. We use the molar mass. How do I calculate the molar mass of sodium nitrate? Okay, sodium weighs, nitrogen weighs, oxygen weighs 16 times. So that's 48. So if we add those together, you said 85? So we have 85 grams of NaNO3. One mole of NaNO3. So our grams are going to cancel out. We're left with moles of NaNO3. So how am I going to use that to calculate nitrate? Mole to mole ratio. I always look at him and he always tells me the right answer. Look at that. So, and we know that is 2 to 2, right? You could put 1 to 1. It means the same thing. But I always put what's in the chemical equation so I don't make silly mistakes. Okay, oops, sorry, that should be NO2. Good eye, good eye. Okay, so we just need to subtract for the molar mass. We just need to subtract that 1 oxygen. So I believe that would be 69, right? Are we almost there? Okay, who's doing the heavy lifting? One point two or 117? 217. 1.217. Okay, How many sig figs should I have? 3. So that would be 1.22. And that's grams of NaNO3. I mean NaNO2. Yeah. Okay. So now I know that this is my theoretical or ideal. This is my ideal. So if I want to figure out the actual, what do I need to do? If I have the percent yield, I multiply it by it. That's right. So I know that this here is my my theoretical or ideal. So my actual times 100 equals 95%. So then I get 1.22 times 0.95. And then that's going to give me my answer. Which is like what? 1.17?
How'd you get 9 of the actual?
How did I get 9 of the actual?
Oh, that says actual. Oh, never mind.
That says actual, yes. That says actual. That's an A. Sorry. Sorry about my third grade handwriting. So is it 1.22 times 0.95 is what? 1.7? 1.17? 1.16. Okay. And then if we do sig figs, here we have to take this into consideration. So it'll be 2 sig figs, so it'll be 1.2. 1.2 grams. NaNO2. Okay, questions, concerns, cash? No, it's 1.2 grams. Yes. No, it would be grams of sodium nitrite. Okay, questions? No questions? Okay, so we talked about limiting reactants, or I often will call them limiting reagents, right? So I gave you guys the example of the cheese sandwich, right? You guys remember that? For those who don't. So if I have 8 slices of cheese, oh, first off, we have to get the chemical formula for making a cheese sandwich, right? So 2 pieces of bread, that's right. 2 bread, 1 cheese. Yields 1 sandwich. Oops. So if I have 8 cheeses, and 20 pieces of bread, yeah, we did. Just doing a refresher, you know. How many sandwiches can I make? 8, right? So that means that what is limiting? Then what is an excess? Okay. Piece of cake, right? So, in chemistry, we do this all the time, right? Here's an example. So if I have 3 carbon atoms and I have 2 oxygen molecules, how many carbon dioxides can I make? 2, right? And we'll have 1 carbon that would be unreactive, right? So the moral of the story is the thing that we have the least amount of, the least quantity of, will run out first, right? Okay, so let's do a problem. Calculate the mass of antimony 3 iodide SbI3 that can be produced by the reaction of 129 grams of antimony and 381 grams of iodine. Find the mass in grams of the element that will be left. Where am I going to start? Am I given? Got it? Chemical equation. So we need to start with the chemical equation. So what are my reactants? Sb and iodine. Iodine, just I. Are you sure? I2. Why is it I2? It's diatomic. That's right. And that's going to make SbI3. Okay. So is it balanced? Nope. What do I need to do to balance it? Two Sb. 2 here. 2 here. 2 there. And 2 here. Okay. And a 3. Okay. It's balanced now, right? Okay. So since we have 2 reactants, we have antimony and we have iodine, we have values for both of those, right? That should tell you immediately that we have what type of problem? What type of problem is this? What was that? I heard somebody say it. A limiting reagent, right? So we have one of these guys have to be limiting, right? So we just need to figure out which one is limiting. So do we take the mass or do we take the moles or quantity? The moles. So we have to figure out the moles. Okay, so if we have 129 grams of antimony, how much does antimony weigh? You got to speak louder because I'm hard of hearing. 121.76 grams. That's right. Speak in your big boy voice. That's right. Okay, so then this is going to give me the number of moles of antimony that we have, right? This is what we actually have. Okay. So somebody do the hard math for me. .06 moles. of antimony. Okay, and I'm going to remind myself that this is what we have. Okay, so if this tells me how much antimony I actually have, I can figure out how much of the iodine I'm going to need to completely react all of the antimony, right? Can't I figure that out? How would I do that? The ratio, right? Okay, so I'll start off with my 106, 1.06. When you said I use that mole to mole ratio, so the mole to mole ratio is what, 2 to 3, right? 2 moles of antimony to 3 moles of iodide. So what do you guys get? Is it 1.59? So this is what I would want to have a complete reaction. This is want. So, but we need to figure out of how much iodine we actually have. So how would I do that? No, that's what we want, right? Because we're starting out, that's how much we would need to completely react all of the antimony. That's how much iodine we need to completely react all of the antimony, right? So we want to have 1.59. But if we want to figure out how much we actually have, we have to start off with what we're given. Okay? Oh, okay. Yes, 381. Is that what you said? I'm sorry. Okay, so what is the molar mass of iodine? So it's 126 point what? 126.9. So we'll say 127, but there's 2 of them, right? So that'll be what? 254 grams. That for 1 mole. Yeah, that's not working out too well. Let me move things up. Okay. Okay, so if I do that math, that gives me how many moles of iodine? Is that 1.5? So this is what we actually have. Okay. So if this is what we actually have, but we want it 1.59 is what we wanted. So which one's going to be limiting? The iodine or the antimony? The iodine, that's right. Good job. So iodine is limited. Okay, so now that we know that the iodine is limiting, we can use that to calculate how much antimony iodide we can actually make, right? So we use that 1.5 moles of our iodide. Do this over here, 1.50 moles of I2. So what is the mole to mole ratio of iodine to antimony iodide? Antimony 3 iodide. So a 3 to 2 or 2 to 3 mole ratio. So that's going to equal 1 mole. I'm running out of room. So if I wanted to calculate the mass, I'll use that 1.00 moles. And what is the molar mass of antimony iodide? Antimony 3 iodide. Oh, it's a new thing. I calculated the moles. I stopped at moles and then I went down and I used the 1.00 moles. That's a 1.00. So over here, 2 over 3. No, because we're looking at antimony. I mean, we're looking at iodine to antimony 3 iodide, right? So we look at the chemical equation. If we have 1.50 moles of iodine, that's what we're actually using. That's our limiting reagent. So that's going to let us know how much we can actually make. And it's like the cheese. The cheese ran out first. This is going to run out first, right? So we have to use that to calculate how much antimony 3 iodide we can make. So we look at the ratio. It's for every 2 antimony iodide, we have 3. You see that up here? Yeah, you got it? Okay. Yeah, so the iodides are going to cancel out, and then we're going to get how much antimony iodide we can actually make. Okay, so then, what was that? Where do you guys get? Where are you guys getting 2 to 2? Oh yeah. Okay, you guys understand that, right? Yeah. Okay. Okay. Okay, so now we need the molar mass of the antimony iodide, antimony 3 iodide. So we know the antimony was 121.76. And then we know that we have 3 iodides. So then that's 3 times 127. Okay, so that's 1, 2, 6, so 8, 3. So 381 plus 121. So then that's 6 point.
I got 502.76.
Thank you. .76 grams of SBI3, 1 mole of SBI3, and that's just going to be 502.76. Of SBI3. Okay. Okay, so that gives us how much of the antimony 3 iodide we can make, right? Okay. Yes, because we wanted grams. We want the mass. When we ask for mass, we want grams, right? Anytime you're asked for mass, you want to give me grams. If you're asked for moles, you want to give me moles, right? Okay. So the next part of it, they also want to know how much is going to be left over. Now, the law of conservation says what you put in, you have to get out in terms of mass. Okay. So if we added up everything that we put in, so we have 129 plus 381. And then we subtract how much we actually make. That's going to give us what's going to be left over, right? So we made 502.76.
$7.24.
7.24. Thank you. And that would be grams of antimony, since we know that the antimony was what was in abundance. Okay. Welcome to the real world. No, real world. This is what we have to calculate. Okay, so let me explain to you guys this, right? So, in terms of things that happen in life, right? You guys take medicine. So, if somebody gives you the calculation and figure that out for medicine, how many people think that? Do you guys remember?
We can't hear you, Dr. Henry.
So, in the 80s, there were manufacturers that had these errors in how much drugs they were adding to chemical reactions, and they packaged them. There's about 355 people who died because of that, right? So it's the real world, right? How many of you guys are planning to go to medicine? So, who do you think does the calculation for the administration of drugs to patients? The nurse, right? The nurses are the ones that are doing the calculations, right? Yeah. 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 And it happens routinely, particularly exactly. Yeah. 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 So those are things that you want to keep in mind when you guys are in the field, that you want to make sure that you double check your calculations, right? Okay, questions, concerns, Cash. Okay, so the next couple of slides are the same problem, but done different ways. There's about 3 or 4 different ways that you can do this problem. Yes, sir. I think my way is the easiest way, but I've given you 2 other ways to sit there and do it, all right? So I gave you my way, and there's 2 other ways within the lecture notes themselves. We're not gonna go over those. You guys can take a look at them on your own, right? Okay, so here's another way of doing exactly the same problem. And you come up with the answer the same way. So, I mean, you come up with the exact same answers. Okay, so that brings us to the next problem, or our next topic, energy. So we talked about the law of conservation in terms of mass, and we've been focusing on mass, and I've been pounding, law of conservation, law of conservation, law of conservation. At the very beginning of class, we talked about energy as well, the law of conservation of energy. Well, we need to talk about the units of energy first, right? So the units for energy is, SI units is joules. And what a joule means is basically the force of 1 Newton applied over a distance of 1 meter. The units are 1 joule is going to be equal to 1 kilogram per meter squared, second squared. So what does that mean to us? We use calories. You guys heard of calories? Yeah, everybody's watching your calories, right? Okay, so let's talk about those calories, right? So energy required to raise the temperature 1 gram of water 1 degree, okay? So that's the definition of a calorie, not the food calorie. Talk about that in a second. But the general definition of a calorie is the energy that's required to raise the temperature of 1 gram of water 1 degree, okay? And that could be a degree of Celsius, or it could be a degree of Kelvin, because it's the same thing, right? It's that change. So 1 calorie is going to be equal to approximately 4.18 joules, 4.184 joules. So we could say our conversion factor, 4.18 joules per calorie. A kilocalorie is, a kilojoules is just 1,000 times a joule, right? A kilocalorie is 1,000 times a calorie. And so when we're talking about large quantities of energy, we typically talk about kilojoules or kilocalories. Now, when we talk about food calories, and we represent that with a capital C, cal, instead of a lowercase c, cal, a food calorie, 1 food calorie is going to equal 1,000 calories. So 1 capital C calorie is going to equal 1,000 small c calorie. Okay, so when we're talking about food and it says it's 100 calories, capital C calories, how many calories is that really? Little c calories. So 100 times 1,000, right? Okay. Okay, so let's see if you guys picked up anything. So calculate the number of kilocalories, calories, and joules in 42.5 kilojoules. So what are we going to start off with? Our given 42.5 kilojoules let's do joules first because it's the easiest, right? So how many kilojoules are in a joule? Right. So 1 kilojoule is going to equal 1,000 joules. Is that right? So if I have 42,500 joules, how many calories is that going to be? So what is the relationship between joules and calories? Okay. So that'll be 10,500 and something. 10,100. And what is the next number? Okay, so 10,000. So for 3 sig figs, it'll be 10,200, right? Okay. Okay, so if I want to change that to kilocalories, I'm going to need to do what? Divide by what? 1,000. That's right. So I also should tell you this. One of the reasons why I'm so sensitive about when people say, "Oh, it's just chemistry or whatever," right? Is because my grandfather died in the hospital because of a nurse's mistake, right? She gave him the wrong amount of drug, and so he ended up dying, right? And he went in for something that was routine, right? And that's the bad part. And so I am very sensitive about that, right? And particularly, I think it's your responsibility. You decide that you want to go into healthcare, it is your responsibility to make sure that you're doing your job, right? So I am extremely sensitive about it. So I can't remember the drug. I was really young when I found out. I don't know, and my grandmother couldn't have told me in the first place. But he actually went in. He went in for he had a little cyst on the inside of his thing, and they were getting ready to administer or to go in for surgery. They actually overdosed him on the drug, and they didn't catch it till well after the fact. So he was already dead when they came back. So, yeah, but you know, it's one of those things that happen, and that you don't think about, you know, until you're in that situation. And the key is that you don't want to be in that situation. So I hate when people say, well, you know, this is chemistry. It's not the real world. No, it is the real world. You need to know what you're doing. That's right. Yes. And you're right. It is multiple parties involved, but it's usually the mistakes are usually done at a particular level, right? And that's the thing. And so there always should be checks and balances in systems, but a lot of times they're not, you know. And you know, in areas that there is health disparities, you have more incidents of things like that happening, you know. So rural areas, you know, so yeah. Okay, off my political soapbox for the moment, back to science. Let me clear this. Okay, so how can we use this, right? So that's what we're getting to next. So the next thing that we're going to be talking about are thermochemical equations. So we've talked about thermochemical equations at the very, very beginning, right? Thought you would never see it again, right? Talked about endothermic and exothermic. What does endothermic means? Endothermic means in, so we're putting energy in, right? Okay, exothermic would mean so then we're releasing energy, right? Okay, so if we think about a fire burning, it's going to be, so it's going to be an exothermic reaction. Good job, good job. Okay, so now how will we write this in terms of the chemical equation, right? So that's what you guys are going to learn here. So there's two ways of doing it. So the amount of energy, now that you know what the energy is, we can use this symbol. This here is called the enthalpy. Enthalpy. E-N-T-H-A-P, A-L-P-Y, enthalpy. Okay. It's a word, yes. It's a word, and it basically means it's like energy, right? But it has a special meaning because it's energy per mole. Okay, that's what it really means. So this here, the delta H, represents that enthalpy, or we often will call it the heat of the reaction, right? Because when we think about energy in terms of chemical reaction, we have to think about heat because that's how we notice it, is by that heat, right? When a reaction is really hot, we know that it's exothermic. If a reaction is really cold, then we know that it's endothermic, okay? So the way that we show that it is being released in a reaction, we give it a negative sign, right? That basically means that it's being released, okay? What it actually means in terms of the chemical equation is that the energy, this amount of energy, is on the product side, okay? This would be another way of showing that exact equation. Okay, do you guys see the distinction right there? Okay, now if it's endothermic, it's going to have a positive value for the delta H. So that basically means that we need to add that energy. So that's why we use that positive. Okay. So when we write the chemical equation and we put it in as part of the chemical equation, we put it on the reactant side. Okay. So for endothermic, it goes on the reactant side. For exothermic, it goes on the product side. Okay. You guys are with me? Okay, good. Okay, so the thermal decomposition of limestone. So we have solid calcium carbonate, CaCO3, to lime, solid calcium oxide, and gaseous carbon dioxide is an endothermic reaction requiring 178 kilojoules per mole. Okay, so what we want you to do is write the thermochemical equation in both forms. Is it Got it? Okay, good. So first thing that we want to do is to do what? And then that's going to make is it balanced? Yep, it's balanced. Okay, so if I want to put it in the equation, how would I write the energy? I'm going to put it on the reactant side. And you should always write, talk about enthalpy, it should be per mole, right? And it's typically based upon per mole of whatever is, well, in this case, of the carbon, calcium carbonate, right? Okay, so the other way of writing it would be what would be the other way? Delta R. So that R just stands for reaction, right? And sometimes you don't write the R. Most books, they don't include the R, but it's an R. So would it be a positive value or would it be a negative value? Okay, it doesn't want to move for me. There you go. Okay. Piece of cake? Okay. You said, okay. So now this is just how we would write the chemical equation. Now the next part is how we're going to use it, right? So let me show you how you're going to use it. Okay, oh, let me take a step back first. Okay, so it's going to be used exactly the same way that we've done everything with stoichiometry. Okay, so we need to use the number of moles. It's based upon the number of moles, so we can use the number of moles to do the calculations. So if we're given the energy and the enthalpy, then we can calculate, use that to calculate the number of moles. Okay, so let me give you an example. Okay, what mass of liquid in octane CH18L, a component of gasoline, must be burnt to provide 9.05 times 10 to the fourth kilojoules of heat? Delta HR is equal to minus 5,471 kilojoules per mole of octane, in octane. Okay, first thing that we need to do is to do what? First thing that we should do. What do we do for every other equations that we had to? Chemical equation. Okay, so we have gasoline burning, or octane burning, C8, H18. We know that if it's burning, it has to require what? Oxygen. That's right. And then we're going to make CO2 and water. Okay. Okay. How many carbons do we have on our reactant side? Product side? Hydrogens? Reactant side? Oxygens? Okay, is it balanced? No, I'm not. Okay, so how do I balance it? Okay, so then that will give me 8 carbon. How many oxygens? Okay, is that balanced? No. Okay, so then what do I need to do to that hydrogen? Okay, so then that gives me 18 hydrogens. And then how many oxygens? 8 times 2 plus 9. 25. Okay. Okay, so what am I going to do now? What did we do earlier? Why not we just do 25 over 2, right? 25 over 2. Okay, so now, normally I would say you can't cut this in half, but we're talking about the molar scale, right? We're planning to use it on the molar scale. That means that we have a whole bunch of it. We also know that this is based upon 1 mole because the enthalpy is based upon 1 mole of this. This is already set up for 1 mole. So in this situation, and particularly in thermal chemistry, if you have a half reaction, you can leave it in the half reaction form. Okay. So then, is this endothermic or exothermic? It's exothermic. So then I know it's going to be on the side of the equation, right? Okay. So we have this beautiful equation now. Now we're starting out with our given. 9.05 times 10 to the 4 kilojoules. Oops, yeah. So then I can use this, because it's part of my equation, to calculate how many moles of C8H18. So for every 5,471 kilojoules, I get 1 mole of C8H18. Then if I want to change that because they want the mass, 1 mole. We have 8 carbons. Carbon weighs 12 times 8. Twelve times 8 is 72. And 18 hydrogens, hydrogen waste. So 114. What? No, it shouldn't be times to the negative. So we have 9.05 to the fourth power, right? Okay. And we're dividing that by, or multiplying it by 114. So sig figs, we should have and that's kilojoules. Oops, sorry, no, sorry, kilograms, my bad. Not kilograms, grams. Oops. Grams of C8H18. Almost, let's see, quite a bit. Okay. Yes. That's right. Because if it's a negative, that means it's exothermic, it's being released. If it's positive, that means it's endothermic, that means it is going to be on the reactant side. That's right. Okay. Questions, concerns, cash, Kool-Aid. Okay. Okay, so we're going to take another 5-minute break. On the final, you're going to see a couple of those on the exam. Stoichiometrically, no, it'll be, so typically if they're looking at big picture for the final, it's big picture that they're looking at, right? So if you look at the questions, most of them are big picture, and usually it's going to be very straightforward. Either you're going to balance chemical equations. Most cases, the chemical equations are going to be balanced for you, except for when they want to test whether or not you're balancing the chemical equations, right? So then you're going to be given, in a lot of cases, they're going to start you out with moles, right? Because they want you to find the number of moles or find the number of grams. So you'll have one less step to have to do, right? That's right. And that's typical of it. And again, it's big picture. You guys know the material, don't overread it, okay? 9 times out of 10. So in areas that we're in the country, right? So when we talk about problems, we talk about problems normally, right? When the people who write the test talk about problems, they don't talk like normal people do, right? They've been sitting in labs their whole life. They've had, this type of education and all of this stuff, right? So what you have to do is break down what they're saying. A lot of times it's deciphering, translating, right? So like, for instance, my Spanish is horrible, right? You'll be talking to me in Spanish. I won't have a clue as to what you're saying. Although I understand Spanish a little bit, if you go slow, I may understand what you're trying to say. So a lot of times what you need to do is go slow, break it down, and try to figure out what it is. Okay? Because usually you know the stuff. And this is what I find. I've been doing this we've been doing this task now for like what? 4 years? 3 years. 3 years that we've been doing the ACS test. And it kills me because my exams will be 50 times harder than the ACS test. And then there'll be a question is, tell me which one looks like a molecule. And on the board, let me give you an example. Let me get whiteboard here. Oops. So they say, tell me which one looks like a molecule, right? And then they'll do something like this. They'll have, oops. Okay, now which one of these are a molecule? A, B, or C? Which one is a molecule? A, right? Do you know how many students will miss this on the exam? Right? And it's not because you don't know it, because this is one of the first things that you guys learned, right? You know that a molecule is 2 or more, right? Okay. But the first thing you're like, oh, and then you freak out. And then you're like, you just made that mistake. And I'm not kidding. That's what happens. But it's that wording. You guys will get caught up in the wording sometimes and then just kind of throw the question, right? Yeah. So the best thing to do is when you look at it, look how things are worded. And there's kind of like a systematic way of wording. And how many of you guys took the SAT or the, you guys did, right? So in high school, right? So it's the exact same thing. Usually it's just that tweaking of words, and it throws you off and you're like, what the hell am I doing, right? And then, so you want to look at it in that context, okay? And it drives me crazy. I'm like, man, you guys know this. I'm like, this is what, man, I have to give you problems where you have to bleed, sweat, and tears. And then you guys, these easy ones, you're like, here's an easy one for you. And you're like, okay, I'm going to miss this one, right? So take your time. Again, you're going to have time to finish. I'm going to give you time to finish, okay? Okay, so let's talk about solutions, and then we're going to briefly go over solutions. A lot of this we're not going to go over, but I'm trying to give you stuff that you need. Speaking of that, so solutions. Okay, can you guys see the screen? Okay, so we know that a solution is a combination of the solvent and the solute. We've talked about that last week. Solvent is what we are dissolving our solute in, okay? So often the solute is going to either be solid or a gas. Sometimes it can be a liquid, but usually it's the one that we have the least of, okay? So our solvent is typically, in most cases, for our cases, has been water, right? Aqueous, right? So here's an example. So here we have a solution of sodium copper chloride, and we're dissolving it in water, right? So this is our solute. This is going to be our solvent. When we put it together, we get a solution, okay? So we have concentrated and diluted. So have you guys seen those little Kool-Aid bottles that they're liquid form, right? The little small ones, and you squirt it into your glass or whatever, right? Or it's Milo that you put in your water, right? So that's called a concentrate. It's concentrated. Or in the old days, they used to do it with juices. They used to freeze the juice, put it concentrated, and you have to pluck it into water. You guys remember that, right? So that's called a concentrate. It's called concentrate because you have a lot of solute, large quantities of the solute in the solution, right? So that's concentrated. Diluted basically means that it's watered down, right? Like cocktails. Have you guys been to a bar and somebody's just diluting your drinks and you pay top dollar for it? You're like, you really want to get messed up that night? And you're like, no, oh yeah. Or yeah, the ice melt, exactly, yeah. So that's diluted when you have a little bit of the solute and then a lot of the solvent, okay? So this is an example of diluted and concentrated. So in the case of the diluted, we have the copper wire, and this is the silver nitrate. You guys did this experiment, right? Here we have concentrated silver nitrate and then the copper wire. And so you can see by it being concentrated, we get a lot more precipitation of the silver coming out of it, right? Solubility. Solubility is just the measurement of how well the solute dissolves in solution, okay? Now, at a given temperature. Now, this is sometimes a function of temperature. Temperature plays a part in this. Have you guys made simple syrup? Yeah. Sugar and water, right? And cook it, right? So if you put a whole bunch of sugar in water, it takes a while for it to sit there and dissolve, right? So if I sit there and I dilute it, if it's more dilute, then it's going to take less time for it to dissolve, okay? So saturated solutions. Solution is considered to be saturated if the concentration of the solute is pretty high and you're reaching a level that you're beyond the solubility. So it's no longer able to dissolve. So for instance, if I have you guys had warm salty water? Gargle with warm salty water, right? So if I pour a bunch of warm salt in there, right? That salt is going to stay. But if I plan it right, I can get all of that salt to dissolve, right? And so we reach a point where if we add just a little bit more, we'll start getting salt at the bottom, right? And nobody likes that salt at the bottom because then you're just having salt, right? So anyway, so that would be a saturated solution when you're reaching that point right before you start getting everything to start staying solid, okay? Unsaturated basically means that we're under the saturation point or the solubility point. Supersaturated. So supersaturated basically means that normally you have your solubility limit, and now you've done something that allows you to put in a little bit more, okay? Now let me give you an example. So this solution initially was supersaturated, and as soon as we added just that tad bit more, it starts getting crystalline structures. Have you guys ever made crystals, like with your kids or your nephews or nieces or sisters or brothers, right? Those little, none of you guys did? Okay, you can go online on Amazon, you can get it for about 10 bucks. It's a great thing to do with kids, right? So all it is that you make a super saturated solution, and then you're just gonna add just a little bit more, and you actually start forming the crystals, right? And so what happens is that as you drop that one in, it starts to nucleate completely, and everything starts coming out of solution. It's pretty cool to see. Okay, miscible versus immiscible. Well, miscible basically means that it's soluble. Immiscible basically means that it isn't soluble. So oil and water. We know that oil and water is not going to be soluble, right? They're going to be separated. So that's going to be immiscible. So this is an example of immiscible. This is an example of miscible. So when things are able to be dissolved in each other. Okay. Okay, so this is going to be dictated in a lot of cases by polarity. We've talked about polarity real quick. So just a reminder, when we talk about polarity, we have the distribution of charges, something that's partially positive and partially negative, like water. You know that water has a bipolar nature. It has a partial positive and a partial negative. So we know that we could sit there and use water to surround something like sodium, the sodium ion, because then the oxygens will surround that plus charge. And then in the case of the chlorine ion, the hydrogens will surround the minus charge. So let me show you. So you guys can see that here. So here we have the hydrogen surrounding that minus charge, and here we have the oxygen surrounding that plus charge, because they form poles, that partial positive and partial negative. And so that allows things to be dissolved in solution, right? Okay, so if you guys play with salt, go home, warm salty water, put too much salt in there. So typically what happens is that salt will stay. That basically means that you reach the saturation point, right? So once you reach the saturation point, what happens is, oops, got carried away. What happens is that the salt will actually start dissolving. Parts of it will dissolve, but other parts of it will come back and precipitate. And so it forms what we call an equilibrium, okay? The rate of it going in solution is going to be equal to the rate of it coming out of solution. They're going to be equal to each other. Okay, now what kind of dictates this is going to be intermolecular forces. Intermolecular forces, do you guys know what the interstate is? I-5, yes, like I-5. You guys all know what the interstate is? Now I'm going to ask you something. Does I-5 just go through California? Right? It goes to Oregon and it goes to Washington, right? So it's called interstate because it goes through all of those states, right? So that's the reason why we call it interstate. If it was just in California, we would call it intrastate, right? So intermolecular basically means it's between molecules. So if you have it acting on molecules acting on each other, it's between molecules, okay? So then we would call it intermolecular versus intramolecular. That is so tiny. Intermolecular basically means it's within that molecule only, okay? So antifreeze. Antifreeze is ethylene glycol. Ethylene glycol is dissolvable in water. Often we have to dilute our antifreeze to actually use it, right? Where if we put oil in water, it doesn't dissolve, right? It separates, okay? And that's because those intermolecular forces. One case, ethylene glycol is also polar. So then it forms polar interactions and they interact with each other, so it's dissolving in there. Where the oil doesn't interact because they hate each other, right? Hydrocarbons are hydrophobic. They're scared of water. They hate water. They don't want to be around water. They want to stay separated. Okay? So other things that affect solubility is partial pressures. So your partial pressure is going to also affect it. So in the case of if we have room for that partial pressure, so if there's space within the container and there's room in for partial pressure and everything like that, your things aren't going to go back into solutions. They're going to have a hard time getting back into solutions. But as soon as you start compressing that solution, the closer that they get, the more pressure that's building up, you're going to have things that are going to start going back into solution. Okay, so by putting pressure, high pressure situations are going to cause things to go back into solution, right? So that's also going to affect your solubility. So in the case of gases. So for instance, soda, right? So if we have the cap closed on soda, right? It forms a homogeneous solution. Homogeneous means what again? It all looks the same, right? So homogeneous basically means that it all looks the same. As soon as I open that cap, what happens? The gas starts escaping. We start seeing bubbles. Is that homogeneous? No, because then it's trying to escape, right? So we basically allowed that pressure to escape, right? So then we're able to get the bubbles to come out, right? Or partially come out. So okay, so temperature also affects solubility. This basically shows that. So normally we'd have a solution that's soluble, and then as soon as we put in cold water, it starts to precipitate, right? So that means that it's affecting our solubility. So that brings us to concentrations. There are a couple of ways of determining concentrations. One of them is molarity. I'm going to be talking about molarity most of the time. I will talk about molarity, because that is the most commonly used. Another one is percent concentration mass. Percent concentration mass is just the solute over the mass of the solution. Mass of the solute over the mass of the solution. Or we also learn percent composition, which is the part over the whole. It's exactly the same thing, because in the case of the solution, it's the solute and the solvent, which is the whole, right? So, and the solute is just the part. And then we multiply it by 100. Okay, I'm not going to have you do these problems right now, because I want to talk to you guys about molarity. You guys can do those on your own. Okay, molarity. Molarity is moles of solute over liters of solution. We've talked about this in 3 labs now, 3 labs. Moles of solute over liters of solution. Okay, so we're going to be looking at moles of solute over liters of solution. Let me give you a problem. Calculate the molarity of a solution made by dissolving 15 grams of sodium hydroxide in water and diluting to 1.00 times 10 to the second mils solution. Okay, so what am I going to do? We're going to use the molar mass. So we need to find the molar mass of sodium hydroxide. So what is the molar mass of sodium hydroxide? Sodium, 23. We have 1 oxygen, oxygen, 16. And we have 1 hydrogen. So 40 grams per mole. So we have 15 grams. $40 grams for 1 mole. We cancel out our grams. And we get our number of moles. Are we done? No. Okay, somebody do that heavy lifting for me real quick. Okay, so what else do we need to do? Convert our milliliters to liters. So we have 1.00 times 10 to the second power milliliters. We convert that by dividing by 1,000. milliliters. That's going to equal 1 liter. So then we're going to get 0.100 liters. Okay, then how would I calculate molarity now? Okay, molarity is going to equal to 0.38 moles over 0.100 liters. It's 3.8 molar. Okay, piece of cake, not too hard, right? So we can actually use this to determine our number of moles, right? That molarity determine our number of moles if we have liters or milliliters of solution, right? So like for instance, in your problem from your exam, how many of you guys have done problem number, pull up your exam. Okay, number 2, right? So there are 2 things that we need to notice about this problem, right? Well, a couple of things we need to notice about this problem. So the first thing is that it says in a lab exercise, you did an experiment where you are reacting 300.0 milliliters of 1.000 molar ammonium sulfate. So if I wanted to calculate the number of moles, how would I do that of ammonium sulfate? I'm given the volume and the, okay? So first thing I need to change my milliliters to what? I need to change it to liters. Okay, so So 300.0 milliliters has to be changed to liters. I know I've been driving, I've been writing like I've been drinking. No, I wish. So I divide that by 1,000 milliliters, and then that's going to give me my liters. And then I have 1.000 molar, which I know means moles per liter, right? So then I could just say 1 mole over 1 liter, right? So then the liters are going to cancel out. So then I have 0.3000 moles. Okay. Now, but the first thing I should have done was to do what? Before I even did chemical equation. So let's write down the chemical equation. You guys help me out here. So I have ammonium sulfate. What is the chemical formula for ammonium sulfate? NH4. And there's 2 of them. Okay. SO4. And it's aqueous. AQ. Plus copper nitrate. So it's 2 nitrates. NO3, 2. Okay. It's aqueous. And that's going to give us what? NH4, NO3, aqueous, and copper sulfate. Let me move this over so we have room. You said copper sulfate. Okay, is that solid, liquid, gas, or aqueous? Aqueous. How did you know that? No, does the SO4 indicate that it's aqueous? The solubility chart says. Where did you find that solubility chart? In the packet. Oh my God. So if I have something that's aqueous and aqueous and aqueous and aqueous, it's no reaction. So that means I don't have to do any of those problems except for showing that there's no reaction. Oh my God. So it's really important that we write out the chemical equations and check to see whether or not. Yes. Exactly. I gave you the rope. So the question is, are you going to use the rope to pull yourself out, or are you going to use the rope to hang yourself, right? Yeah. So then that's what it really boils down to, right?
So how should we answer that? Just
So
there's no
then you would answer, the way that you would answer it is, first off, you would say the type of reaction that it is. The type of reaction with this. It would be a double replacement reaction. And then this would be the conventional equations. You would balance it out. And then you would just go through and show that it's no reaction for everything else, right? So you wouldn't have to do any of the calculations because there's no reactions. Right?
So that would be for C, D, and E. Is that correct?
Yes. So all you'd have to do is for C, D, and E, it's no reactions. And even you could get away with saying, after you write down the chemical equation and you go through and balance it, just balance it for the sake of showing that you can balance it. And then you would say, this is no reaction, right? Because.
Okay.
That's right. Yeah, you would leave it blank since it's no reaction. So an easy 20 points, right? No, not so much the other ones. Now, okay, so let me give you a hint to number 9. See, these are the benefits of coming to class, right? Benefits of coming to class. So here's a hint for number 9. Do it in steps. There are 2 reactions. Do it in steps. There are 2 reactions. Do it in steps. Number 9. For number 9, there are 2 reactions. Do it in steps. No? Yes. And that's what you guys are supposed to do. You're supposed to utilize the tutors, right? That's why I haven't given them the answer key yet. Okay, are there any questions about the exam or about anything else? You can ask me about the exam. I'll tell you what I'm going to tell you. So that question, if you don't get that question, right, at this point, you know. Okay, I will give you a hint to that one too. You need to do the chemical reaction, right? Okay, So then that means that think about what you guys learned today. What did you guys learn today? Excess and limiting. Excess and limiting. So now the first thing that I want to do, right, is you're going to use the information because you have to tell me what metal it is, right? Okay, so if you know what metal it is, then it should be easy to sit there and figure that out because you're given everything that you need. Look at that table. Isn't there a table? Isn't there a couple of tables? How do you get the grams, or how do you? So you got the grams that you used, right? Yeah. So then you have how many cubes, right? And don't you know how big those cubes are? So if you know how big those cubes are, you also know the volume of those cubes, right? Okay. You guys understand? Yeah. So you're using everything that you've learned up until this point for this exam, right? Have you guys noticed? It's a lot. Yeah, you guys have learned a lot. Apparently, yeah, yeah. Okay. Okay, so I'm gonna let you guys go, right? Are you guys cool with that? Okay, good luck, good luck, good luck, and I'll see you guys on Thursday. Do the exam. Don't wait till the last minute.